What just happened? There we go. Good afternoon. Anyone else feel like just canceling class and go get a drink somewhere? And
Yes.
not alcohol, but oh, you could have alcohol. I just don't. So. Okay. Dream on. So today we move into another part of the integral where we're actually going to get the area under the curve. So what I'm going to start off with is just a function. I'm going to show you a program on the TI-84 calculator. I actually have it downloaded on this one. If I had the cable, which I unfortunately forgot at home, I could give it to you if anyone has a TI-84. I will bring it next time. I will load it up and show you maybe how you can do it. But anyway, we're going to go through this. This will do sort of automatically what we're going to do a little bit manually. But this whole lesson really doesn't do anything for us except give us the history of how they developed this concept. When we do it, we'll do it again more accurately on Monday. That's the one we'll use. So this is just one that will sort of build understanding. Okay, so let's get a function. Let's go with something not too complicated. How about 0.5 x squared plus 2x. And so what we're going to, let me, shoot. I don't know if I can get out of there. Well, we'll live with that. What we're going to do is we're going to get a graph. What we're going to do is, what we're doing today is estimating the area under that graph. Now remember, what we're starting with, the function we're going to start with is this is a derivative. So this is a rate function. Whatever's going on here is a rate of change. The area under a function, a graph that is a rate of change, ends up being the amounts. So it's a way we've kind of touched on this, but we're going to do it this way. Not quite sure what we're going to get, but let's see. Let's go from 0 maybe to 5 and partition. So what we're going to do, well, I'm just going to show you. You don't quite know what we're going to do. Usually we start with this and then we tell you. I just want you to see what we're going to do. Let's do 6 partitions. So it's drawn. This is our function, 0.5x squared plus 2x. Okay, so this is the function here, and we asked it to go from 0 to 5. That's our interval. And so what would it look like? How could we get the area under this curve? One thing we could do is we could divide it into rectangles. And what's the area of a rectangle? Length times width, base times height. Okay, so we're going to do that. I'm going to hit enter again. See how this works. Now there's a couple different ones you can do. We're going to do the left sum because in the homework it's doing everything what's called a left sum. And again, I'll show you the picture. It'll kind of make sense once you see what we're doing. Left sum. And I'm going to hit enter. What it did is it's drawing rectangles that go up to the function with the left corner touches the function. Okay. This first one's actually here, it's touching at 0, so notice it's a very slim. Is this an over or an underestimation of the area? It's underestimating the area because there's this, it's not counting these little triangular places, but this is a rough estimate. So that's what we're doing today, is we're going to take a rough estimate by doing exactly this, because what is the area of a rectangle? Base times height. Length times width. And what we do is we're going to be able to figure out that this length, right, this is going from 0 to 5. We divided it into 6 regions. So we take 5 minus 0, which is 5. You divide it by 6, and that's the base. What's the height? The height comes from the function. It's the y value of the function. So we take that y value times the change that we're setting up. And again, we'll go through these a couple different ways. But we're just finding the areas of rectangles, and it gets us close. Okay. How do you think we could get more accurate? Because this is telling us that with the left sums, we got an area of 36, 36.7. How could we get more accurate? Smaller rectangles. So if you do smaller rectangles, that means you've got more of them, right? Because we've still got to go from 0 to 5. Smaller rectangles means more rectangles. So I did 6. Let's watch what happens when I do. I've got to go back to settings. It lets me change the number of partitions. So instead of 6, let's do 35. And we draw again. We go here. We're going to do the left side. There's 35. Does that look more accurate? Yeah, there's less underlap, and we're at 44. So that's what we're going to do is you take more and more. Fortunately for us, most of the cases we're doing 4 or 5 partitions because that's all the calculations. We don't want to do 35 calculations. In the old days, that's how they did it. This is all they had. They would draw a graph, and 500 years ago, this is how they got the area under a curve. It's called Riemann sums. I don't even know what his first name is, but Riemann is credited with this method. So we're going to do that. What I want to show you is that you may not know it, but your calculator actually can already do this. And notice that program, what was cool is it actually put it into my Y1. So that program, it's actually online. I downloaded it. Somebody else wrote it. But it actually puts it in here and uses all the tools. When you go to graph, why is it not graphing? Let's see. Oh, it got turned off because of the equal sign. So I go over here, turn it on. I'm going to graph it. If we want to be absolutely 100% accurate, we go second calc, and we can take the integral here, number 6. And we're going to do this on Monday to get the accuracy. We have to put the boundaries. Let's go from 0 to 5. Let's see, how does that work? It didn't do it. Second calc, number 6. Oh, wait, no. That's the derivative. We want the integral, sorry, number 7. Lower limit is 0. Upper limit is 5. And it actually gets exactly the area as 45.8. When we had 35, it was 44 point something, right? Pretty close. So this is what we're shooting for, is getting to this accuracy. And we're going to see that there's a nice way where we just integrate, and it's a not too bad a way to get to this. But today's lecture, today's stuff, what we're going to work with is those rectangles. Okay, so we're estimating the area under a curve, and the reason we do this is because the curve, remember, is a rate of change curve. It's a derivative curve, so the area under it will represent accumulation, how much sales we had. We've got the rate of sales we're making. If we take this integral, get the area under that, we'll have the amount of sales. Okay. So let's jump in here. So this is Riemann sums. So they give us, and there's a graph they're going to have us work with. We always start with a function, and sorry. I think it's this one. I don't know what my password is, though. Oh, let's just sign in. Okay. So again, I want to just emphasize, how do we know that this function is a derivative? The what? V for velocity, okay. And then the per, yeah. So yeah, V, the speed that something's happening. Good. I missed that. I was going, wait. Oh yeah, V for velocity. Where's that? So that's I think they're using V for volume though, or I don't know. Anyway, but the per tells us it's a rate, right? This is happening. This is a rate, and it's going for the first 20 days. So T is in days 0 to 20, and this is a leak. An oil rig is leaking, and this is how fast, how many barrels of oil is the speed that it's coming out. And by knowing the speed that and again, you can measure that, or they can at least, they'll have something that measures the speed of the stuff coming out. They'll actually be able to calculate how much oil was released from this first 20 days. So the way they do it is they're going to take this function and they graph it. So the good news is it's what's happening to the leak. Slowing down, right? It's slowing down because this is a rate. We don't know how much is coming, but at least the speed it's coming out is slowing down. And if we were going to do a left Riemann sum, how would we do that? So it's going from 0 to 20. So that would be our interval. That was the question, is how much oil leaked out there in the first 20 days. So that's our interval we're going to use. How many divisions, how many partitions do you want to do? 5. Okay, I like it. I was afraid someone's going to say 30, and that's 5 is perfect. Okay, good. So we're going, and again, the more accurate, the more partitions, the smaller rectangles, the better. But 5 is going to give us a better view of what's going on. So what we do is we take 20, or actually we take 20 minus 0, so you take the start and the end of the interval and you subtract them, and you find how long the interval is. So in this case it's 20. We wanted to divide it into 5 rectangles. So what do you think, how long would each rectangle be? Would it make sense that you would take the length, which is 20, divided by the number of rectangles you want to make, and we would find that each rectangle will be 4, a length of 4. Now, it might have been better to do 4, but so what I know is I go from 0 to, let's see, that's 2.5. I'll say this is about 4 here. So I'm going to have a rectangle that has a base this long. And if we're doing a left sum, that means the left corner of the rectangle goes up to the graph, and we come over, and then we would. Now, is this going to give us an under or an over estimate? Over. Right, because this time the rectangle is above the curve for the most part. And what they do is, one method they found is you find the area with the left sum, and then you find the area with the right sum, and if you take the average, you get pretty doggone accurate. Yes?
Why do you take 5?
Because she told me. Yeah. We could have done 6. We could have done, they will tell you. So the 5 is nothing special. It's just we have to choose to divide it in, and in the homework they'll tell you. They'll give you these two. They'll say go from 0 to 20 and make 5 intervals. And then what you're going to need to do is you're going to need to start sort of doing this. So let me just ask you, what's the area of this rectangle here? What's its length? 4. What's its height? 60. So 4 times 60, 240. So this area is 240. Okay. Again, it's an estimate. It's not real accurate, but this is how they did it. And again, they would do either smaller rectangles. Then they would come to the next one, which would start where the other one left off, so that would go here, and that's 1, 2, 3, I think 4 would be about here. So then you'd get a triangle that, or a rectangle. Maybe it's a little too long. Let's see, that's 1, 2, 3.5, 4. Well, this should be a little bit shorter, but we'll say that that's still 4. What's this height? Somewhere between 40 and 50, right? Maybe 46, maybe 45. It's an estimate. The good news is on the in the homework, when you have to use the graph, you can click on the graph and they'll give you those amounts. So you don't have to guess, because sometimes they're like 45.6. There's no way you could tell. But if you click on the graph, it will tell you. So we'll just say that this is 46 times 4. And we would get that calculation, and we would add that, and notice how that's all we're doing is we're summing up the triangles. So the mathematics is very simple. We're taking the area of a rectangle, base times width, length times height, however you want to do it, and we're just going to make however many rectangles they tell us, and then we're going to add the areas together.
How did you get the first rectangle? Why did it go over the
Because they told us to take a left sum, which means that the left-hand side of the rectangle goes all the way up to the graph.
Why is the next one go to
It also goes up to the graph right here. So notice because the graph is getting smaller, each one successively will come over and till about 4 more. And then this one will go about 4 more.
And then you just eyeball that?
Yeah. And so you see it's not real accurate, is it? So we're going to pick up some accuracy because we actually have the function for this, so we can use our calculator to put these numbers in, and we could count. This is 4 plus 4 is 8, 12. We could figure out what each one of these places is. So this is actually 4. This would be 8. 8 plus 4 is 12. Then the next one would be at 16. So you can tell I'm getting off here. These are supposed to be equal. And then 16 plus 4 is 20. So again, so let's let the text, we'll follow along with them. They're going to take it even slower. They didn't start with 5. They started with 1. So you could just take one big rectangle and make an estimate that it's 60 times 20 is 1,200,000 barrels. Okay, so that's a very rough estimate, right? Very much overestimating, but it's an easy one. Okay, so that's the first one. So then they take a step. Let's say, okay, if 1 gave us that, let's try to be more accurate. Let's do 2. So here's 2. And so the first one goes 10, and the other one goes from 10 to 20. Again, notice this would be 60 times 10, so that's 600. 600. And then this one would be, it's almost 30, probably about 29 times 10. Right? So the base is still, notice that the bottom of the rectangles is always the same length. Okay, my drawings weren't very accurately drawn. What do you think they're going to do next? 3? Oh, they jumped to 4. Okay, so again, we're getting, and you can kind of see we're getting more and more accurate, and that's all they're doing. And if we do 4, then notice these are nice intervals. It's 5, 5, 5, 5. And again, we have to have some way of figuring out what is the height of each one. Okay. Now, if you were taking this in the engineering, they do the same thing, but they do left sums, they do right sums, they do mid sums. We're just going to, all the homework we're giving you, it's always going to be a left sum. So they will look like this, where the left corner of the rectangle is touching the graph. Area under the curve, right? We're getting an area. Well, most of them are under. It is an overestimate. It's a rough estimate, okay? But don't you do that sometimes? Close enough. How much your dad asks you how much you need to go to the movies? You always overestimate, right?
Yes.
I got popcorn. Just could probably get by with 20, but hey, Dad, I need $50, right? That's all. You always overestimate.
So the rectangle should represent
Area.
in this situation.
So in this situation, how many barrels slipped out? Yeah, because this is a rate. Area under the curve represents the amount, the accumulated amount. So this gives us a way to estimate how much oil spilled from that leak over 20 days.
And wouldn't the derivative just be finding
This,
percentage?
it would be the rate, which is actually what we have. The graph is the derivative. It's the rate. So that's it's a little. We have to switch our thinking to backwards how we were thinking before. Before we had the amount and we were thinking of rates of change and tangent lines. Now what we have is really the graph of all the tangent lines at every place. We have the derivative graph, and now the area under it will represent the amounts. Okay. And again, it'll take us till Monday to connect everything. This is really just a technique that we're going to pick up to get you to believe that the area under a derivative graph is the amount. That's all it's, we won't be asked to do this too often. So what this is saying is, notice it's taking the function value at 0 times 5, the function value at 5 times 5, function value at 10 times 5, and the function value at 15 times 5, because we had, again, what we were doing is we were going from 0 to 20, and this is 1, 2, 3, 4 intervals, or 4 divisions. So we start at the left at 0, and to get 4 of them, we did this. 20 divided by 4 equals 5. They each have to be 5 long, so go from 0 to 5, 5 to 10, 10 to 15, and notice that gives us 1, 2, 3, 4 rectangles. We never counted the 20. That would be if we were doing the right-hand side. So there's always one left off.
You go all the way until you can, then add up the total.
Yes. And so they just take the base times the height. That's what this is doing. The function value of 5 is the height of the graph. And if you remember back there, v of 0 was 60. So you take 60 times 5, you got 300. This one must have been whatever the height was at 5. Right here, it's probably about 41, right? And then we're going to take the height at 10, which is about 29, and the height at 15, which is about 20. Okay, so they did all these calculations, and then you just add them up. Add up the areas of the rectangles. We've got an estimate for the area under that curve. Okay, we'll do a few of these together and see how it goes. And okay, and again, it just gets there if we use more and more rectangles. So they become, the more we use, the smaller they become. And this is one where the width is only 2.5, 2.5. And we've got 1, 2, 3. Well, so many we forgot. How many subdivisions? I'll give 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the more we take, the more we get there, the closer we get. And again, we're going to get something that's very accurate when we talk about it on Monday. But today's just to kind of do a little bit of practice. And so right-hand Riemann sums. Actually, we've already drawn on this. I sort of went first instead of second. So what we see is as we get closer, what we're getting the total volume is the area under the rate of change curve. So what that area represented, because it's under a rate curve, is the total amount of oil that was leaked. Okay. So here again, it's a lot of notation, but what you will always get is you get the question will give you what interval you're looking at. Sometimes from zero, this last case was 0 to 20, could be from 2 to 3, whatever. There's a time period you're looking at, and then they will tell you how many intervals, how many divisions, how many rectangles we're going to have. Okay? And then we go from there. Okay? They're going to come up with some notation. The notation's not highly important. We'll get to where we practice, but you'll get, so what this is saying is you're going from some point A to some point B. There's some curve up here, and you're going to divide it into, with left sums, x naught, x1, x2, and these distances are all equal, x3, and so forth. And what we're going to do is we're going to make rectangles that go up to the curve and over to the next one. This one will go up to the curve, over to the next one. And so a lot of curves, you'll get some that will overestimate and some that will underestimate, and so forth. Okay? But you always take the endpoints, subtract them, and divide by however many intervals they want, subdivisions. Okay? So again, just painstakingly, we're going from some interval A to B, and we divide it up, and the distance between the x values is always the same. Okay? And it will be determined by taking the bigger endpoint minus the smaller endpoint and dividing it by however many divisions they tell us to make. And again, they might tell us 5, they might tell us 3. Okay, and this is just getting into telling us that this is called a Riemann sum. Because what are we doing is we are taking sums of the area. Riemann is some mathematician's name from, I don't know, 300-400 years ago, who came up with this idea. And that's what we did. So yeah, this one goes up to 60. This one they identified went up to 42. This one here was 28. This one was 18. And again, we would take 5 times each of these, add them together, we get an estimate for the amount spilled. Okay. You could actually do this without even looking at the graph, if you have enough. In fact, we'll do one that we do that, because if you have the function, you can actually plug in the various values into the function. You would actually get these values, not by looking at the graph, and you'd be able to do the calculation. Okay. There's this notation, you may have seen it, especially if you've taken statistics. It's called sigma notation. It simply means to add all the things together. And I think this fell apart, but it should be something like you're taking the various components of f of the function and you're multiplying them by the length of the base of the rectangle. Okay, so let's let's walk through an example. Let's calculate some Riemann sums. Okay, so we're asked to compute a left Riemann sum for this function. We're going from -1 to 1, and we're supposed to use 5 intervals. So fortunately, it's showing this, but how long is each interval? Again, we take 1, subtract -1, so we take the bigger one minus the smaller one, and then we divide by the number of subdivisions, which is 5. So 1 plus 1 is 2. 2 divided by 5 is 0.4. Okay? So each subdivision, each base is going to be 0.4. Its length is going to be 0.4. So we'll come up here and we'll say whatever rectangle we're having, all of them have a base of 0.4. Where do we start? We start at the left side, -1. So we're going to need to calculate this. They've got them here. -1, add 0.4 to -1, you'll get -0.6. Add 0.4, so each time you're adding 0.4, add 0.4, you get to -0.2. Add 0.4, you get to 0.2. Add 0.4, you get to 0.6. If you add 0.4 again, you get to 1, and we've got the whole interval. Okay, the ones we're going to use for the 5 rectangles: -1, -0.6, -0.2, 0.2, and 0.6. So notice this gives us 1, 2, 3, 4, 5 rectangles. Okay, so what we need is we need f of -1 times 0.4 plus f of -0.6 times 0.4 plus f of -0.2 times 0.4. See, it's just tedious, right? F of 0.2 times 0.4. And then the last one, so how many do we have? We've got 1, 2, 3, 4. The last one will be f of 0.6 times 0.4. Okay. How do we get all these y values? What I'm going to suggest is we can come to our calculator. We can plug in the function, which was x squared plus 1? Plus 1. We're going to go to our table, but we want to get the table set up so that it works like everything. So I'm going to go second to table set. Where did we want to start? -1. How wide is each interval? 0.4, right? That was the 2 divided by 5. So we put in 0.4 here. That's the change in the table. And then we have it on auto. So the table's actually going to do all our work. We don't have to, so it's going to simplify things for us. We put the function in. We get our table set up. The two things we need to know: where are we starting? So that's the left end. And then how wide is each rectangle? 0.4. Now I can go to my table, second table, and look at it's got, when I plug in -1, I get a y value of 2. That's the top of the graph. That's the height of that left-hand rectangle. And it will draw it. We'll actually look at the graph and we'll be able to draw this. -0.6, the function value is 1.36. And so I've got all my values here. And so, let me make this a little bit smaller. Maybe not too small. I can actually do all my calculations. I'm going to take let's go back here, right? So we wanted f of negative 1 is going to be 2. So that's that one right here. Times 0.4 plus f of negative 0.6, which is 1.36. That's the y value, times the base of the rectangle, which is 0.4, plus 1.04 times 0.4 plus 1.04 times 0.4, and finally plus 1.36 times 0.4. Okay, so we could add all these together, multiply and add, and we will have an estimate for the area under the curve. Okay, and that's what you're going to be doing during this homework. Okay, that's one of the things, is you're going to take all these together. Now, one thing that makes this a little easier is, notice we're multiplying each of the terms by 0.4. So what could we do with that 0.4 to make it a little easier? Instead of having to multiply 5 times or 4 times, 5 times, couldn't we factor that out? So we take 0.4 times 2 plus 1.36 plus 1.04 plus 1.04 plus 1.36. We have 1, 2, 3, 4, 5. They asked for 5 rectangles. We have 5 heights. Okay, so we can now add these together. Let's go ahead and do that. 2 plus 1.36 plus 1.04 plus 1.04 plus 1.36. I think I got them all. 1, 2, 3, 4, 5. And we get a total of 6.8. And we multiply by the 0.4. And again, you could have done it individually. This will actually give you the areas of the rectangles, but it's a little bit faster to do the calculation by factoring the base out. Okay, so then we take 0.4 times 6.8. Oops. Is 2.72. And what is that? That is the area under that curve. Okay. I'm going to look at the graph going from -1 to 1. We don't have to go too high, so maybe just 3. What we just did is we've gotten an estimate for the area under this curve. Okay, we could have actually partitioned it off, and I guess I can go back and use that program. We use x squared plus 1 from -1 to 1. We're going to do 5 partitions because they asked for it. There's that. We hit enter. They're going to ask for left sums. There's that. That's the visual of what we actually came up with. And notice we got 2.72. 2.72. This one we did without doing the graph. We just knew that the graph we would have these various y values. But if we look at the graph, does it make more sense that what we're getting is area is rectangles? You don't look convinced. We'll try. Yes, sir.
Are the areas, so on the left side of the y-axis, the parts that are coming outside, that are overestimate, are they equal to the underestimate side as well?
They could, yeah, on this one they probably are. So a lot of times you actually get very accurate because exactly the overestimate takes care of the underestimate on the other side when you have symmetry. Good. So if we were to do this, find the exact one, we're probably pretty close. And so that's why they came up with these methods, and then they could say, hey, we're going to be pretty accurate with this because we've got an overestimate here but an underestimate here, and it looks like it'll balance out. But again, as you saw in that program, there's actually many different ways. You could do a right-hand sum, which the rectangles would be matching up over here, but we're just going to stick with this left-hand sum. Okay. 343. So we're almost there because it's basically, you'll just need to kind of practice it a little bit. Okay, so, and if you look at the slides before I break them all up, they also show you everything. So they give you the picture of what happened, but notice we actually calculated this without even looking at the picture. We knew the interval, so we get the length of the interval, which ends up being 2. We want 5 subdivisions, so we divide that by 5. And so we've got our 5 rectangles, and if you'll set up, once you get those numbers, if you set up your calculator, your table, it'll do all the calculations for you. You're going to add all those y values together and then multiply by the base, because that you're just basically factoring out the base. Okay, so let's look at, and that's what they did here. So we jumped the gun a little bit, but they just found all the y values, and then since they're all getting multiplied by exactly the same number of 0.4, instead of doing that 5 times, let's just factor it out and do it 1 time, and you actually get the same numbers. Now, if you don't feel like, really, am I getting the same number? Try it both ways, and you'll see each time, because if you distribute it back through, you actually get the same thing. Okay, and notice they came up with exactly the same value we got. Okay, so this is where, again, yeah, you could do a lot of things without a graphing calculator, but having a graphing calculator on this particular one is going to be so powerful. And knowing how to use your table feature, right? Setting it the left, whatever the left boundary is, that's where you want to start, and then you want the table to change by whatever your rectangle's base is. Okay, and we can calculate that. All right. So here's the homework also gives you stuff like this. In fact, I took this is exactly out of the homework. You're going to have to estimate again, but I believe if you click on the graph itself, it should give you the points that you need to get, because you can see we need to go from 0 to 24, which is over here. So that's going to go to 0 for 24, dividing it into 4 regions. So how wide is each rectangle? Again, we take 24 minus 0 divided by 4, because we want to divide it into 4 pieces. That's 24 divided by 4. Each piece should be a length of 6, which is a convenient amount because they've got the graph labeled in groups of 3, so it's a little bit easier to pull out the 6s here. Okay, and so the first rectangle we're going to draw, we start at 0, because that's where it says to start, and we're doing a left hand. We go up to the top of the graph, which is 10, and we go over 6. So there's 3, and there's 6. And we go straight over, horizontally over. We don't follow the graph anymore. We only follow the graph to get that left corner point. Okay, so we've got this. And so what is the area of this rectangle? It's got a height of 10, base of 6, it's 60. So we could start doing that. Where does the next one start? Where the other one lays off? Yeah, about there. So it starts at 6 and it goes to 12. And now we're going to have to make an estimate. This is 2, this must be 4, 6, 8, and 10. So this is 2. I don't think it's quite 3, but you could maybe call it 3.
So we're going to do like estimates or
No, we won't have, because again, we're not going to do too much of this on the test because we're going to get some techniques that you'll get the exact values. This is just sort of a building block. But this one is where, yeah, you'd have to click on the test would tell you, let's say it was 3. So that's 3 times 6, which would be 18. And again, if you click on the graph, it'll give you the exact value. We've got this next one here. It looks like we're exactly at 2. And again, we go 6. So that's 2 times 6, which is 12. And then at this one, we're going to go here, up to the graph, and over 6. And again, that looks like it's a little bit over 3. So I'll just estimate it at 3, which is another 18. And notice we have 4 sums. And we actually were calculating the areas here, so we've already taken the height times the base. So those are the numbers. We just add those together. That's our estimate for the area under the curve. Okay, that's an answer we're going to provide. 10, 20, 30, 90, 108. Okay, so that's those. There's a couple of these where they give you a graph like this, and you just have to do that. Now, if it doesn't accept that exact answer, again, click on the graph, and they will probably give you the exact values of this. This might be 2.7, and this one might be 3.3 or something. Okay, they'll give you those exact values. If they give you the function, we're able to use that with the graphing calculator. Okay, but it's not really we're doing calculus so much. We're just doing geometry. We're fitting in rectangles into these curves. Yes. I will put the file in Canvas. I have it in my other class, so I do have it saved. You'd have to download it, but you also have to go to TI Calculator's place and get their connect, be able to connect your computer to your calculator. You'd have to have the cables. I've got a transfer cable between the two, so I'd be happy to transfer it over to you, but we're not going to do it too much. You'll see there's only a few that you're going to have to do. So it's, for me, I like having it to demonstrate it because I can show you that that's all that's going on, but for doing the homework, it's not that helpful. Okay. Uh-oh. What does it mean when there's no more slides? It must be done. So start working. I think there's 7 problems. All you're doing is estimating it. And remember, hopefully it builds some understanding that when you have a derivative, the area under the curve gives you the amount that has accumulated.